I appreciate the opportunity this afternoon to discuss with you an incredible project that we've designed at the Park School. It's the Science and Engineering Wing edition. So today we have a few learning objectives, but most importantly, we're going to tell multiple stories about the design and the ultimately planning and construction of this edition. So to start, we will cover objectives such as the design strategies for achieving a low EUI building, which means how can we reduce the energy consumption of the building. We're going to walk through how the systems, the facade, the MEP help reduce those energy loads and improve the occupant comfort. And finally, we're going to talk about the strategies we use to really make this building an active teaching tool that helps support Park in their STEAM education. So as with any great project, we had incredible partners that helped us make it possible. Just real quickly, Morabito Consultants was the structural engineer, BKM Engineering, MEP, DMW was our civil engineer, FSI did the energy modeling for us, CapEx was the owner's rep, and Southway Builders did cost estimating and were the construction manager for the project. Just a little bit of background on the Park School itself. It is a PK through 12 independent school, just north of us here in Baltimore, Maryland. It has about 800 plus students. And their kind of ideal is they're driven by curiosity and empowered by perspective. So before we dig into the details and the data and the processes that we went through to design the edition, I want to tell the story and kind of set the context of the campus, talk a little bit about the goals and the purpose behind the project, and really allow that to lead into the decisions that we created together with the school. So the Park School is in this idyllic setting at the foothill of some rolling hills just north of downtown Baltimore. The heart of the campus is the Park Pond. The buildings and the campus are kind of surround the pond, and it is both the kind of the figurative and the actual heart of the school. We got started in this with the school by revisiting and updating their master plan. And through discussions at the master planning level, we knew that the school wanted and needed to expand its science and engineering classrooms. And through a series of iterations, we landed on what was determined to be the best place for that addition. And that happened to be right in front of the athletic center at the end of the iconic pond here at Park. And we knew that that this place, the building site here, had a lot of heat and a lot of, I would say, importance to the school community and to the site itself. It was very prominent, and that really led us to a series of interactions to determine really what it should be, how it should interact with the site, and how it can contribute to the building and site context to really create a space and a place that looked like it had always been here and really became a part of the campus. So with this kind of importance to where the building is placed, the school, along with us, came up with the guiding principles for the project. They need to be mindful of the future, socially and environmentally responsible, really take clues and make educational opportunities, and be transformative space. So with the importance of the site within the Park campus, we started by actually backing up and looking at the site and its place at 30,000 feet, and really with the school understanding its spirit of place. what really makes this physical environment, the symbolic nature of what this place is, and how can we contextualize that into the built form. So in the view that you see here on the screen is the aerial of the campus. It is almost a campus under one roof. The building on the very left-hand side, just to the right of the bright blue pool, is the athletic center, and the addition of science and engineering goes in front of it. The pond may be just slightly hard to see. It was green when Google flew over that day, but it's just to the left of the large parking lot, and that is really where the focal point of the campus and what is becomes the bookend to the science and engineering addition. So within that, the tree line to the south of the image is a creek called Moore's Branch, and it was this idea of how Moore's Branch leads into further becomes a tributary and leads into a larger ecosystem where it flows into the Jones Fall stream, and the Jones Falls flows into Chesapeake Bay. So the impact that one would have at the edge of the park school makes it all the way down into the Chesapeake Bay. And that is really what set the idea of the purpose of this project, was understanding how in one's context and determining one's purpose, choosing how you can contribute, and the small contributions that you make affect a larger system. And the ending result was an addition that was at the end of the pond in front of the athletics, that connected the athletic building to the upper and middle school and truly made Park a school under one roof. The building, as you can start to see here, and we'll get into further for the rest of the webinar, interacts and has access down to the pond, across over to Moore's Branch. It also has the idea of how to start to frame views, both to the east to the pond and to the south to the woods. And it's really about nestling this building into the existing context while looking at a couple key contributors to really understand, again, this idea of how one contributes to a larger system. So today we're going to look at that question in three ways. We're going to look at how and what it means to be net zero energy ready, how we made spaces within the building flexible so that as pedagogy shifts, either during the school day, school year, the space can accommodate for that, or how it's set up to be flexible as pedagogy changes over time. And most importantly, we're going to discuss how the building facilitates connections. These are connections between students, between student and faculty, between students and the subject matter of science that they're studying, and between their connection to the natural world. But we want to start telling the story of how to make this building net zero ready, and go through our methodology that we used with the Park School and our consultant team to get that ready and to be set up to be net zero ready. So our path to net zero energy at a large global scale is really two parts. We want to get the energy use as low as possible, and then offset what is left with renewables on site. So when we think about how to reduce the energy use as much as possible, it goes into two buckets. The first is rethinking the orientation and the massing, and that was really decided and really fleshed out at the master planning process. So we focused our efforts on reducing energy by looking at the envelope, the systems themselves, and the controls, and really understanding what was the best payback and what made the most sense for this specific institution on this specific site. So to help accomplish that and really guide us through this process, we have what we call ECMs. energy conservation measures. And it were these measures that we worked with the school and our consultants to flush out, to understand what they were. And this is how we took the path to get this building to be net zero ready. So what is an energy conservation measure? It's really it's a method of increasing energy efficiency within the building. And at Park itself, we had 13 different measures that we looked at, and they fell under the envelope, again, the systems and controls. And for each of those 13 measures, we did a cost-benefit analysis to identify which measures save the most energy and how cost-effective would those measures be. And it was all going to help us and help the school determining the payback period. We did this with our full consultant team. So both with the client and their facility team, our design team, and specifically lots of input from our energy modeler and our cost estimator, which was the contractor specifically. And the reason that we did this is that we wanted to make data-driven design decisions. And that is important throughout the design process because we wanted to shorten the feedback loop. And a lot of times, if there are design professionals on this webinar, a lot of times we will, for instance, on the fins that you'll see on the eastern facade, we will work with our engineers to understand, all right, if those fins were 18 inches deep or 12 inches deep, or what the frequency of those, we could run the energy model and understand, how much of the sun we are blocking and how much of effect that has on the overall energy consumption of the building. But what makes this, what we did at Park slightly different is that we had the cost estimating money to go with that. So not only were we running energy modeling on these up to 13 measures, but we were also identifying the first cost and how much energy savings to offset that first cost within the ECMs that we decided as a group. And that led us to really understand what was the best confluence of energy savings and cost savings together. So to run through this with the client in an abbreviation version here today, we created a really fancy spreadsheet that I will try not to bore you with too much, but just really hit the key ideas of when we think about specifically the envelope, taking the glazing value, the wall insulation, roof insulation. We also looked at the window to wall ratio, but we tested different systems, different amount of insulation. We understand how much energy savings we would get from that, what that would pay back on an annual basis, and then understand what the added first cost of those elements were. And we found out very quickly that, adding more wall insulation or more roof insulation actually didn't have a considerable effect on either the amount of energy saved or the simple payback in a number of years, where it took 50, 60 or more years to pay back the cost of that additional information. So if we zoom in on just one of the ECMs, specifically the type of glazing that we use. So we ran the energy model on up to 5 or 6 different qualities of glass. We ended up settling on Solar Van 70 with its higher U value, but still had a high level of visible light transmission. You can see that overall, this selection of glass saved 8.7% of the energy savings of the full project, and then that per year saves just under $1,000 in energy savings. And the simple, with the added first cost over the code base requirement, the payback for this specific ECM came in just over 14 years. And we did the same again with the systems, HVAC, lighting, and specifically for the science and engineering building, we looked at the the fume hoods in the science labs. What was unique about the Park School site in this method of figuring out how to reduce energy usage the most, there wasn't a silver bullet that was presented itself because of the really tight site. The really optimal high efficiency MEP HVAC systems such as geothermal that we typically use on buildings was not possible here. The site available land wasn't there, so we had to look for ways of getting energy usage savings with a more typical and we'll say basic at the moment system. We settled on a VRF system with a heat recovery for the classrooms that had modest, really energy savings overall. What we found was, but through the control systems of occupancy sensors and light daylight sensors as well from the lighting control, we were able to reduce energy use through the control side to offset the more baseline VRF system. In addition, one of the things that we paid a lot of attention to, because this was a science lab, or had science labs in it, was that the amount of energy used by the types of the fume hoods. We worked with the school to understand how their process, how they would use the fume hood day in and day out and during the class period. And we went from a constant volume of air exchange to one that had a variable volume that allowed it to use to kick on and off as the class was going in, the fume hood was in use. That really set up from an efficiency standpoint a considerable amount of savings, more from the operational use of how the school would use the fume hood, and that allowed us to use, again, the variable volume air instead of a constant air, which produced a large amount of our overall savings. And then we looked at the renewables and understanding how much energy we could produce off of the addition roof and also off the neighboring roof of the athletic facility right behind us. So at the end of this process with the school, we looked at different combinations of these ECMs. We looked at ones that had the best payback, were the best performers, were the best performers that also reached net zero by including the photovoltaics. We also had the option that we presented to the school that there was enough roof area for the PVs that this could be a net positive building and actually be regenerative. But overall, we saved roughly 23% of the baseline energy use, and a vast majority of that energy savings came from the HVAC controls, the glazing, and then the type of exhaust that we use with the fume hoods in the science labs. So in a way, our baseline savings in a high level summary, energy savings without the PVs came to about $2,500 of energy costs per year. We got our EUI down to 22.9, but the path to net zero with the additional first cost of the PV panels, both to make it net zero and net positive, came the simple year over year payback for net zero came in at 9.5 years, and to make it net positive, slightly higher at 12.9. And that was key because as we started the conversations and throughout the conversations of this process, we were looking for a payback, or the institution was looking for a payback of around 10 years to get back to zero cost. And so we were able to get the PV array and using the conservation measures that we decided got us just under the 10-year payback at 9.5. We're going to shift just slightly and talk about the building and the space itself. Really, the net zero energy pieces folded in and were added on top of the planning that went into the science and engineering addition, and really how the flexibility and the spaces and the combination of the spaces work together. So as I mentioned at the very beginning, the Park School was almost a school under one roof. The last two buildings that weren't connected were the Athletic Center, which was separated originally by a outdoor plaza, to the middle and upper school building shown here on the bottom right-hand side. So this addition connected those two buildings and really slid in between, creating a new lobby and entry point, both for the gym and the upper and the middle school to plan south. But on the first level, in a more open floor plan, were two engineering labs for electrical engineering, and then one for a wood and metal shop. Both of those spaces have the ability to spill into an outdoor classroom, a covered outdoor classroom here marked in D. But with the site improvements, we are able to create an amphitheater and allow multiple paths down to access and be near the Parks Pond and to the bridge across to Morris Branch, which you can see here on the left-hand side. So just a few images of the first floor. Here's the lobby when you first come in. It acts as a pre-function space for the athletics, for before and after school pickup, and is really the connection point to the middle school and upper school, and really the rest of campus to the right-hand side of the image itself. And if you were to turn around and looked in, you can see the electrical engineering lab with the large window that looks out to the lobby. It puts the projects that they're working on display, so it allows everyone that comes to the school the ability to get a sneak peek of the incredible work that the students at the Park School are doing. And again, has that ability to connect both back to the lobby, but also to the covered outdoor classroom. So through the planning kind of process, we knew that the engineering labs wanted to be on the first floor to really have access for material delivery and drop off. But the science labs themselves were designed for the upper school students. So the building that we connected to on the level one was the middle school, but the second level was all upper school. So there was a synergy for the science labs to be located on level 2 of this building. And whether the square footage didn't quite match up, it allowed us for these really unique outdoor spaces. So that in this case, you can start to see the outdoor space to the left-hand side of the view here, where it's created a covered space with the science labs on level 2. And if we look at the floor plan of level 2, it's really creating several pieces into the design and planning specifically of the science and the science floor of this addition. So it starts on the right-hand side with a student collaboration area that really is that knuckle that leads you to the rest of the upper school and leads you down a collaborative science corridor with soft seating, room for student collaboration before you enter the science classrooms themselves. We spent a lot of time working with the science faculty at the Park School to understand the best combination of the prep room, individual project rooms for long-term science experiments, and how the science labs themselves can be flexible and work with each other in pairs. One of the decisions that we made right up front was really to give the addition space as much space as possible for collaboration in the science labs, that we were able to take space within the existing building for restrooms, mechanical space, the elevator, and really let the the addition be for those kind of key student-focused areas. But as we work through the lab configurations with the science department, a couple of kind of key factors always rose to the top. The science labs themselves wanted to be flexible and interchangeable. So as we worked through the options and in the final configuration, all the casework and all the fixed elements along the perimeter, allowing the center of the space to be reconfigured as much as the school wanted during the day, but also given the flexibility for what is coming in the future. The prep room wanted to be accessible by all 4 classrooms, so it had needed to have access from the corridor, but through discussions that really it sets up in sets of 2 labs. So each set of 2 labs opens up to each other and has access to a fume hood located in the central prep area. So through those iterations, we ended up with the final lab configuration in the floor plan here on level 2. And as I was mentioning, all the casework, the gases, utilities along the perimeter, each set of the 2 classrooms open up to each other, and they also have access to the project room. So one of the discussions we had with the science faculty was that they wanted the ability to run, for their students to run longer term projects, science experiments that would last more than a class period, or even maybe longer than a few weeks. They needed an area that they could set up these capstone projects to allow students to really get engaged and get in depth into problems that they were exploring and trying to solve. So to accommodate that, each set of the set of science classrooms has a project room that's fitted out just like the science lab workbench within the science lab itself, but it gives the school the opportunity to set either individual students or collections of students together to run longer term experiments, and allowing the science classrooms themselves to be flexible to continuing to teach multiple science disciplines within each of the spaces. And some quick views of the science labs themselves. You can start to see the casework, the utilities along the perimeter. There's a movable partition with a writable surface that separates the sets of 2 science labs. You can see there previously in the closed and now in the open. That allows for group instruction of 2 classes and group experiments as the teachers needed throughout the semester. As mentioned previously, we talked a little bit about the fume hoods and being centralized within a central prep space. That allowed for the faculty to set up pre-experiments and do the prep that is needed before a class and in between classes. But we were able to find ways of connecting these rooms together by aligning the fume hoods in an axial configuration through the prep room. You can see on the picture on the right that you can see from one science lab through the prep room and into the other. Just a way of making connections both internally between the science labs, and just a way of really showing again that what you're doing in one space is bigger than that by allowing differing levels of visual and physical connection. And the same is also true for the project room. So with the counter, with the dual counter, one for a working surface and one that has the utilities behind where this photo is taken, but it has direct views into the science corridor and out to the outside, overlooking the woods and the pond. And again, giving students the ability to run those long-term experiments, but it also gives the ability for all the students walking by to see and understand the cool stuff that is happening within the science department. And then at the end, really is the space is also about bringing students together, creating a student hub specifically for the upper school, a place for them to hang out before and after class, a space for them to do group study, group work, group project work. So a mixture of hard and soft furniture, giving students really the flexibility to choose the seating option that was most comfortable to them at that time, and the options to choose different seating, throughout the semester. And then the science corridor too was set up in a similar way. So having a combination of soft and fixed seating allowed for group work to happen before and after the science classes, but also just a space for those students to hang out. So in the last piece here, when we talk about facilitating connection, it really, for us, focused on how we can make a space as clean as possible, so really that the activity going on inside can be unencumbered by in a way by the architecture. Really, how can we design the building and organize it in such a way that those collaboration areas really had the unobstructed view to the pond, into nature, and really in any building, there's always one piece, one part of it that is special, at least one. And for us in this project is really the science corridor. So we spent a lot of time thinking about the structural, the MEP systems, how that was laid out, so that when you're in this space, you can really get a sense of how the environment interacts with the building and how you can see out and make those connections to the site and allow space for students to make connections with each other. And it really evolved around the idea of having these fins on the exterior that were important from our energy conservation measures at the beginning of the presentation, but also allowed this ability to have the dappled light for students to be within this space to see as the day and hours changed, how the shadow pattern changed within the space itself. And even had the ability to see the rain chain from that diverts water from the roof into the bioretention basin that eventually feeds into Moore's Branch. But it put all of this front and center in kind of the clearest way possible. So in the planning of this specific piece, the first decision was actually the most key. Building up against the existing building, it is essentially a single loaded corridor addition. And the question becomes what space should get the natural daylight? Should it be the science labs themselves, or should it be within the corridor? Working through multiple iterations, we landed, I think, in the right spot where the direct daylight is in the corridor and then has filtered through large glass entries into the science labs and some up high clear story light. But that was kind of the key first decision of the addition, was what space received the direct natural daylight. And then as we got further in, we started looking at the structural framing. We wanted to see if we could remove as many columns as possible from the exterior edge of the building and really making that as barrier-free visually as possible. So we created a structural bay system that cantilevered to plan south, that picked up both the roof and the floor plate of the second floor, really to have this science corridor as clean as possible. And that gave us the ability to really have just the glass and then the shading from the fins be that exterior barrier. And in doing so, you can start to see in these construction pictures how the structure was at the column at the corridor line to the right-hand side, allowed the unobstructed view from a structural perspective on the left, and how we had to hang the solid portion the exterior wall above the storefront. And all of this hanging of the structure, along with the pattern of the storefront mullions, the fins, the pattern of the ceiling baffle, all came from a common module, allowing it to line up when you're looking at it in one point. So the whole building is built off a 3'4" module. So the exterior storefront, the fins, and again, the baffles, and even the structure up above allows that all falls within that module. So during construction, we set a common line, common dimension off the column grid to start laying out these specific building elements one at a time, allowing them to line up to, again, kind of make that connection to the exterior as clean as possible. And then the final piece of the design puzzle for this was how to handle the mechanical zoning. The larger units for the addition sit actually on the athletic center roof, just planned north of the addition. But we wanted to create and really compartmentalize all the ductwork for all the spaces as much as possible. So over the prep room and the storage, chemical storage in the center of the space, and then branching out left and right into the entry portals into the science classroom is where all the ductwork and terminal units live. And then it's only the branch ducts that serve the space that come out from the center blue space that you see here in that RCP. And then, as you can see in these cutaway perspectives, in that entry portal from the corridor into the science lab, we dropped the soffit to create that portal, but that is where vast majority of all the valves, the ductwork, the terminal units live. And then in the corridor itself, it's only the single ducts needed to provide the fresh air, heating, cooling for the corridor space. So really, again, a process of trying to keep that space as open and clean as possible. And then really at the end, the solar fin and the pattern was a design exercise all unto itself. Throughout the project, we started with a curtain wall for the exterior glazing and ended up switching to storefront. And I mentioned that only because the fin itself was originally planned to be attached to the curtain wall. But as we switched to storefront, we had to work with the product rep, in this case was Thunder Max, and our structural engineer to create a system that would allow it to attach to the building, not at the storefront, but above and below. So working collaborative, we came up with a bracket that attached two brackets, one above and below, and a channel that captured the fin that allowed it to basically free span the 10 feet of the glass zone within the storefront. And then we created a custom pattern for the perforation itself. Working with the graphic design department at the Park School, we took their tree logo and simplified it into the starburst that you see here on the screen itself. And we took half of that and we ended up mirroring it and rotating it to create the leaf pattern that you see in the fin today. And it's that idea that's part of the Park School that's creating the dappled light within the space. And so finally here, just a few images at the end of the finished building. You can see the science corridor with the perforated fins with the light coming across. You also get a sense of a cantilevered gutter from the butterfly roof that ends in a rain train that directs water to the bottom into the bioretention structure. And then spinning around from the other side, again, you see the pattern of the fins at the second level, but you also get a sense here of the site work and the site design of having outdoor seating that brought you down. And on the left-hand side, you can see we lowered the front wall of the bioretention area so that faculty can bring out the science classes and the students can see the media, the plants that are within that bioretention area up front and get their and up close. And then finally, ending on the view across the pond again, with the science classroom, the corridor up above, the butterfly roof, really trying to capture the ethos of the Park School and allow the building to complement the faculty and become a partner and being a teaching tool for their STEM education program.